I can't see it. This one's hard to visualize. So let me talk through the problem solving process that I did here. Okay, so first let's start out with reading it. Let R be the region enclosed by this graph and this vertical or horizontal line. The x coordinates of the points of the intersection of the graph are x of 1 and x of 2. Interesting. Why are they telling us this? X of 1 is less than x of 2. Yeah, I don't know why they're talking about this yet. Then it says, which of the following gives the volume of the solid generated by the region R? Okay, so we know what it should look like. We know that our integral should be the area, and we're going to be doing the integral with respect to x because we see that we have a horizontal axis of revolution. And we know for this, because it's an axis of revolution or a volume of revolution problem, we know that our area function is pi r squared. So we're going to have a pi, we're going to have an r, and it's going to be squared, all with respect to x. And we're going to need to have an x sub 1 down here and x sub 2. Ooh, maybe that's why they have the x sub 1, x sub 2. Anyways, let's move forward. Let's draw a visual here. Now, I know that this polynomial function it has a degree of 4, which means both the endpoints will be pointing in the same direction, just like a parabola. And it's negative, so it's opening downward. The x to the 4th is negative. Okay, that's how I know it's opening downward. And then we have this line right here. Now, when I first thought about it, I'm thinking like, shoot, how do I know that this 3 over 2, this y equals 3 over 2 line is not above this curve, So how am I supposed to visualize this area? And that's when these guys come in. Because it tells us that they intersect each other, I don't have to go through the process of trying to figure out if there's an x value that when I plug into this, I can get 3 over 2. I don't have to figure that out. The problem just tells me. So let me fix this line. Let's move it down. They intersect at x of 1, x of 2. I don't even know if my graph is exact as according to the axes, but it should look something like that. All right. So let's finish our visualization. It says that we're revolving around the 3 over 2 axis, which is good news because that means we can use a disk method. The area of our region is touching the axis of revolution, so we're not going to have to use the washer method. We can use a disk method. Okay, and this is what it would kind of look like if it started revolving. That's a little small for me. I should have made this bigger. So let me give a bigger cross section here. The goal here is to find the radius. How do we find this radius right here? If you have looked at the formula or you've practiced this before, you do the outer function minus the axis, and that will give you your radius. And so I'm going to put the outer function minus the axis of revolution, which is 3 over 2. And that's going to be my radius. And so now I just got to plug this sucker in. We know that the radius is squared inside our integral. Our integral is with respect to x. And don't forget the pi on the outside, the scalar. And then we have, of course, our lower bound and our upper bound that was given to us in the problem. And I think you guys can see our answer. Now, I have to do a caveat here really fast. Technically, it doesn't matter if you go axis minus the outer function. And the reason why that doesn't matter ultimately is because we square it. You square it. If you square a negative or a positive, you're going to get the same result. However, I think it is traditional to do the outer function minus the axis of revolution. Okay, so it looks like we lucked out. This radius right here is found right there. Now, these ones are trying to, like, this one kind of looks like a washer method, okay, and you might want to put it, no, that's not right. The radius has to be squared. This is the radius, and that's what's being squared. And that's how you do that one.